Hello everyone. This is Zhongwen Xu. I'm from CA Lab. So today we are going to have, I think, a very brief introduction to the reinforcement learning, and also we have another second part of the lecture in tomorrow afternoon, Singapore time, and so hopefully I think people can get some sense about what reinforcement learning is. And also I have some coding code reading session in the later part of this talk. And I think not only people can learn from the theory and mechanism of the reinforcement learning, but also people can really put into efforts to see how they can use reinforcement learning. Okay. So first of all, there are many great materials to read, and actually this is the first time I really give a complete lecture about reinforcement learning. So I would like to let you know there are a bunch of very great materials available free online, so that you can all have a much deeper understanding of reinforcement learning after these lectures. So first of all is the very classic the reinforcement learning book. So Introduction to Reinforcement Learning is written by Rich Sutton and Andrew Battle. So it's the published version here is the second version. So it has incorporated many recent advances and also rewriting the book compared to the, I think there was another much earlier version. The first version that was also very classic. So I would recommend everyone to read the book. And actually many of the content of this lecture are from the book, and so does many other classic lectures as well. So the second one is the very popular reinforcement learning lecture introduced by David Silver. So David Silver is the main developer and leader of the Breakthrough AlphaGo and also AlphaStar. So he taught this course, and when he was at UCL, so it was back in 2013. So deep reinforcement learning wasn't popular yet, but he is a really great teacher and lecturer. So this one is highly recommended. Also later and more recently in 2021, just this year, so DeepMind and also UCL at London, they collaborate and have a very good reinforcement learning lecture as well. And also please check out UC Berkeley's circular veins lectures. So these are all great materials. Yeah, and for my current lectures, so the disclaimer is that content was adapted from the IR book, also from some of the above mentioned lectures. So the copyright belongs to all of these original authors and can be only used for pure educational purposes. Yeah, so let's start. First is about the fundamentals of reinforcement learning. So it's basically about what reinforcement learning really is, and what are the formal formulation of the key concepts of reinforcement learning. Yeah, first of all, reinforcement learning is in I would say reinforcement is a subfield in the wider field, which is artificial intelligence. So different researchers and different people have various understanding of artificial intelligence. But here, I think we can make a very clear statement about what we think artificial intelligence is, especially in the context of reinforcement learning. So the following concise statement is that we think artificial intelligence is the field is to study the AI so that the agents or the AI can be able to learn to make decisions to achieve goals. So there are like three different very important paths in this statement. First one is to learn. So learning is very important because learning allows you to really adapt to a different situation, and also to like, instead of like handcraft rules, which is predefined, learning allows you to really like change the behavior from the data, and also to self-correct the behavior of the agent. And the second one is make decisions. So if we think like artificial intelligence, one of the key important property of artificial intelligence is that it can really like consider like what it perceives from the world. It can produce the decisions, so, and also the reactions. And the ultimate objective of the artificial intelligence is to achieve goals. So it's similar to like human beings. We have like different goals, like in different stages of our life, and also like maybe during your study and during your work. And even like into your daily life, you have different goals. For example, like just finishing your lunch and also attending this lecture. So these are like all kind of different goals, and they are in different granularity, but all of them are the like a sum of the representation of artificial intelligence. So if we think that like by putting into this really concrete concept and divide it into like different important I think concrete definition of artificial intelligence really help us to understand why like reinforcement learning is unique and important in the research of artificial intelligence. So yeah, here are some of like more concrete explanation of what I meant on the like different concepts. The first one is like why we need like interactions in reinforcement learning, because actually from what we observe, like people and also animals, they learn and they adapt themselves by interacting with our environment. So we can consider like the environment is our like actual real world scenario, and like all our daily life is by interactions. So you may consider like people, like the process of people growing up from baby and to like teenagers, and also to adult, and then later stages of the life. Also for the animals, same, like so they grow from like relatively younger and then to elder. So from all the process, they really increase and to grow their abilities, various of abilities, including their recognition of like the visual concepts, like in the baby stage, like people can really barely understand like what are the words, and they can but by interacting with the world, and also provide like the parents will provide some feedback to the babies, and then in this kind of process also like giving some reward back to the baby or the animals. They can learn like what kind of behaviors are good by the rewarding that, or like they can learn what kind of behaviors are not good by receiving possibly like negative reward or even zero reward. So interacting is really the key to allow like the agent or the AI to have like real-time experience with the world, and also to the wider environment. So There are many different other areas in the field of artificial intelligence. So what really make reinforcement learning unique is that it is in a form of active learning rather than passive learning. So what I mean is that compared to, for example, other fields, including like supervised learning or unsupervised learning, the difference is that, like in supervised learning, the typical scenario is that the AI or the model, they are given a fixed data set. So, for example, some classic data sets in image classification include like OAMLS or CIFAR-10, or like even larger data set, ImageNet. So all kind of these supervised learning tasks, they are considered as like passive, because like the input source of these models, they are kind of in a fixed form. So for example, in ImageNet, you have like 1 million images and with like 1,000 classes. So this data set is like fixed, and all the model or like the neural net have to learn from this data set instead to just iterate through this data set, like one path by another, and then to see whether they can increase the classification accuracy from this data set. So this whole procedure is passive. So is that like there are no interaction between the model to the data set. So it's like it's only the model by itself to train itself. It only receives the input with like the input pixels. Like we can consider this as X, and then also the labels, they are Y. So what the model is doing is that to just forward the pixel inputs X to obtain some predicted label, and then to compare with the actual label to see whether they are correct. And then if they are not, it will form some loss, and then to train the model with the loss. So there's nothing like really feedback from the model back to the data set. So reinforcement learning is really different in a sense that the AI or the agent, it is actively involved in the loop. So the environment, so where the environment is, or like where the world is really, it would be affected by the agent itself. So it's a very active process rather than a passive receiving process. So another one key aspect is that the interactions between the agent and the environments, they are often like sequential. So it's so we will take the ImageNet as another case. Another time as example is that like the classification from the image to the label is only like one time. So it's not like we predict these images and then there will be another image after that will affect the results. So there's no any time concept in the classic like image classification tasks, but instead in reinforcement learning, the time really matters. So the interaction are sequential, so which means like the later decisions can also the later interactions can fully depend on the earlier ones. So for example, currently I'm sitting here and giving the talk in this lecture. So if I make a decision like to walk out of my room and then open the door and then go downstairs and then take a walk in the small park near my apartment. So this will really change all of the observations around me. So the observations and also the world I perceive will immediately become like the scenarios in the park. For example, flowers, grass, or like the trees. So very different from what I am now. So this kind of like this can be captured by reinforcement learning, but instead, like in supervised learning, you can barely capture this kind of sequential dependency. Another important perspective of reinforcement learning is that one important thing about our understanding of like human being or some natural animals, we are like goal directed. So in some sense, like people have some goals, long-term or short-term. So reinforcement learning is a good way to really capture like the definition of goal. So we will see later that reinforcement learning is a very general framework. You can use some scalar reward to capture like what to achieve for the agents. So instead of like telling the agent like how to achieve that, we really can use this general formulation to tell the agent like to achieve higher rewards and then achieve the goal. And the fourth important part of the reinforcement learning is that the agent can learn like without the examples of optimal behavior. So compare with the supervised learning case again. So the optimal behavior here means like the optimal classification labels of the data set. So for example, like given a cat image, so the optimal behavior for the model is to classify the image as a cat. This is given to the model so that the model can learn from this example to to decrease the loss and then to use stochastic gradient descent to decrease the loss and then learn from these examples. However, like in reinforcement learning, the optimal behavior is not given. So the agent can start from like really random behavior and it interact with the environment without being told what are the right things to do. So even so, like trained from like really random agents, it can still like gradually learn how to interact and how to achieve with higher score. So finally, like yeah, that's what it means. Like we can use some reward signal and then to guide the agent so that the agent can learn from the interaction between the agent and the environments, so that it can achieve like nearly optimal behavior later purely by the interactions. Yeah, some examples of the reinforcement learning problems are like the following. So which include like many real examples here, like just a few of them. So the first one is like managing an investment portfolio. So as we can see here, like the rewards could be formalized as like the gains. For example, like if you invest like $1,000 into that, and like what are the gains you could achieve 1 year later if you invest in like S&P, so something like that. And also you can put another form of reward for the same task. So if like the task is still like investment, you could put an additional reward like beyond the gains. So you can put additional reward like gain minus the risk. So you do not want like on one hand, you would like to have like a higher gain. On the other hand, you will also like to minimize the risk you expose to the the turbulent like financial risks. So to achieve so, you can just simply put it into the reward. So the reward basically tells like what you would like to achieve. Also, the second example is to make a robot walk. So here, like the reward can be in many different forms. The first one is like distance. So for example, like you can So the task, if you make the distance as a reward, the task becomes like the robot has to like walk as far as possible so that it can maximize the reward. So if the agent is trained in this kind of like distance reward, it will try to really like find a way to go far beyond the originals. So if the reward is given as like speed, for example, like, so how far it can run, or like instead of walking. So if you really give the speed as the like single reward, the robot would have to like optimize this so that it can like walk in a very fast speed. Maybe later it will become a bit dangerous. So the reward can be like good, and also it might imply some like safety issue as well. So the third form of the reward in this robot walking task is goal reaching. So which means like it's a very simple example is that consider there's a family like a home robot. It can like walk around the house and then reaching to certain room. So the reward can be defined as like the robot can walk to the kitchen. So if it reaches the kitchen, the reward will be +1. And then if the robot is going to optimize this reward, it will try various passes so that it can reach the kitchen. So that and so as you can see, there are like many different tasks, include the interaction with the environment, and you can have various definition of the reward. And also the final very classic reinforcement learning problem formulation is to play video or board games. So so these are the reason, like the most successful recent breakthroughs in reinforcement learning. The reason is that the formulation of the video games or board games fit the reinforcement learning problem very well. So the reward can be like if you play the board games, for example, Go or chess, the reward can be simply like win or loss. So the agent is given this reward so that it will optimize the win rate and try to not to lose to the opponent. Also, like in another form, like if the game is not, it's beyond like simply win or loss. So you could have a total score of the full video games so that the agent would learn to like really maximize the total scores, just like the human being playing the video games. So I see some question. Okay. Do you want to ask in, hello? Yes, I think I can read it out. So the question is, how does the model know when to stop taking actions? So yes, I will introduce in more details in the later slides. But I think that's a definition of like, in reinforcement is called like episodic task. So there's a terminal state. So you, I think in a very common scenario, you can define when the model can stop taking the actions. So for example, you can, in our real world cases, you can, and take ourselves as an example, you can really like define like a day as an episode, or even like we can say this whole lecture as an episode. So at the end of the lecture, that's the end of this agent. Or like in I think in a like more concrete case. So for video game playing, it's like before the agent lose the life, it can consider as an episode. So when it comes to an episode, the end of an episode, it will stop taking the actions. So is that clear?
Yes, thank you. I have another question.
Yeah.
Is the reward given to the model only at the end of an episode?
No, it can be in every single step. So yeah, I will talk more about that in the later slides, but let's take the video game as an example, right? So win or loss, that's like if you play the game of Go or like the chess, so you will only receive the reward at the end. But for other video games, for example, like simple Atari games or like typical very popular video games like Dota, you can see the changes of the score like on many of the time steps. So it's not really like only appear at the end of the game. It will appear like everywhere. Is that clear?
So if I can clarify, does that mean in a game like chess or Go,
Yeah.
The model does not have any clue about whether the moves in between were optimal until victory or loss condition is reached?
Yeah, you're right. So it will not, I will not say it receives like no reward, but it will receive a reward of 0 before the end of the game.
Okay, thank you.
So this is a very important property of reinforcement. It is called like delay reward. So the agent make many decisions, right? But it will only receive the reward feedback until very like in the very late stage. So that's a very important property of the reinforcement learning research, which make it very hard as well, because you have to reason through what actions lead to the success at the end of the game, right? So it can be like hundreds or even 1,000 steps away. So the agent has to reason through the whole process and figure out what really make to this final success. Yeah. Yeah, also please feel free to ask any questions. Okay, how does the model decide which action was responsible for the reward? Yes, we will learn about all kind of different algorithms to describe this problem. So it's not a simple answer for this problem, unfortunately. Yeah. Is that clear?
Yes, thank you very much.
Yeah, cool. So yeah, here are also like still continue about like some essentials of reinforcement learning. I think it's another like emphasis about some of the key concepts in the previous few slides. The first one is about time. So as you can see, like very different from the like image or dog or cat classification, this kind of image classification tasks, the time concept is very important in reinforcement because like the decisions are sequential, and also as we have just discussed, they could be really long term because like some of the moves you made now may only like have reward feedback many time steps later. And also like as I mentioned previously, it's an active process. So the agent is very actively gathering the experience to help itself to understand the environment. And the fourth point is that as the agent, like in order to deal with this kind of like long term and also very heavily time dependent decision making, the agent has to learn to predict the future. So it cannot be done in the first phase of the experience, of course, but like gradually when the agent interact more and more with the environment, the agent needs to understand like in this state, what kind of like expected reward it can attain. in the future steps if it continue. So it has to really like predict and summarize the future. So this is a very important concept in reinforcement learning, and we will have much more detailed discussion on this. Also, the reinforcement learning has to deal with uncertainty because like it's the environment is actually very stochastic. So it's not really, the environment will not happen identically in most of the reinforcement learning cases. So the agent has to deal with really like changing underlying dynamics of the environment, also deal with the uncertainty of the futures as well. Yeah, so let me see, is there any question? No, oh, cool. Yeah, so let me play this like small video demo, which was from actually a few years ago. It was the first breakthrough of the deep reinforcement learning called like deep Q learning network. We will have like a couple of slides on the detailed introduction of this network. So this is a very brief video demo of the agent training to play a video game. So here from this simple description, you can see like the agent, all the agents given is the sensory input. So it's the screen. So it is given the pixel input of the whole screen. And then the reward is to like is the score. So the goal of this agent is to maximize the score on the screen. Yeah, so here's another very important thing is like the algorithm itself is very general. It does not need to really like hand specify what's the concept of a ball or what kind of controls it can do. All this kind of knowledge is obtained by the interaction between the agent and the environment. Yeah, first is like just 10 minutes of training. As you can see, like the agent failed many times because it's in a very early stage of the training. And for the game, I think you can already sense the rule. It's like you can move like left or right of the pedal, and then it will hit the ball. The ball will reflect and then go to hit different level of the blocks until it can really go through. So it's like after almost 2 hours of training, the ability of the agent like grows. You can see it can play the game like very well, catch the ball like many times. So this is the score of the video games. So yeah, one student just asked like the reward is given, is it really only at the end of the game? So you can see here, so the reward can be defined as like +1 if the score increases. Yeah, you can see the score keep increasing. Yeah, another section of the video demo is like after like longer training. Here is like 240 minutes of the training. So I think it indicates like the agent becomes really strong. Yeah. So yeah, that's a brief demo. And as a reminder, so for this agent, the input is actually the same as human, as the video game to a human being. So the input is also like just the screen. And also the available action is visible to the agent, which is like move left or right or doing nothing. So it's all of the interfaces are the same as the video games to human being. So the agent learn only by like just playing these games by themselves, just like human being as well. I think some like, of course, like there are like guidelines of the games of rules, but people really like read them through before they really playing the game. So they would just jump in and then play the game to see what kind of to understand the game, and then to increase the score they can obtain from the game. So all kind of things are just the same for the agents or the AI here. Yeah. Any questions about the Atari demo? So all good? Cool. Sorry. So yeah, as Professor Lee mentioned in the very beginning, there are many recent breakthroughs in reinforcement learning, also very specifically in the gaming AIs. So the first very notable example is AlphaGo. I think many of you should have known. This I think is a really significant milestone in the history of AI, and people usually compare it this achievement to the achievement of Deep Blue like many years ago. And I think AlphaGo really marks like the power of AI. Like the AI can be really trained to beat the world champions, Lizardo, back at that time, and really can be trained purely from a data-driven way, and then with the power of the deep neural networks, and also combined with reinforcement learning, it can master a game which is like a simple rules, but like highly, I think highly compressed, even with simple rules, and it requires like really high intelligence to play this game well. I think that was the first event like people can really realize the power of AI. So previously, people are mostly focusing on like supervised learning tasks. So breakthrough has been made in like ImageNet classification by the classic AlexNet. However, that was quite constrained in a setting that is only limited in recognition. So it's like given some images or some video or some audio, the AI can tell what kind of things are in this kind of inputs. However, like the AlphaGo events really makes like people realize the AI can do like sequential decision making. So which is a very key formula in the AI. And also I think this like high profile event really popularized the applications of AI, because I think it made people believe in AI, and so that like AI become like widely available these days. And later, in like a few 2 or 3 years later, maybe if I recall correctly, another big breakthrough was made in the StarCraft game. So it was DeepMind again. They built like AlphaStar. So it was really, so StarCraft 2 is a very highly complex real-time strategy game. So it requires like the AI or the agent to deal with like many different inputs, and also to deal with the different strategies of the game. So it's a really highly complex one, and even like human being had a really hard time to understand the game of the rules. And I think after the effort of like 2 to 3 years, like training with hundreds of TPU, like highly parallel devices, and also like thousands of CPU cores, the agent become really powerful and can beat professional players. And another example is the OpenAI 5 on Dota 2. So again, this is a very highly distributed training system. It playing the game of like Dota 2, which is like you have two signs, and each sign has like 5 players, and they managed to beat also the world champion team. And the training system is consists of like 50,000 CPUs on the early stage of the version, also thousands of GPU cards. So these two like giant like training system for the very state-of-the-art reinforcement learning application in video games really like demonstrate that reinforcement learning is highly effective for the complex video games. And for other like applications beyond video game playing or board games, because I think we really mentioned like reinforcement learning is a general framework in artificial intelligence. It can capture many things, including like decision making, and also like the key concepts that you can specify a goal in a form of like reward scalar, and that the agent can be trained to achieve this goal. Yeah, so it can actually unlock many decision-making real-world problems. I will list a few here as some inspirations. There are many applications out there. So the first one is chip placement. So it's actually, I think the illustration is a simplified concept. You can consider the chip here means like the artificial intelligence chip. So this is a very beautiful complete loop. So you train an AI to design an AI chip, and then the AI chip can be used to help training the AI faster. Yeah, so first of all, it's an empty chip canvas, and then it's a step 0 of the environment, and then it can give some signal to the agent. The agent decide where to place certain part of the chip. So it decides what locations. So, and then on second step, it also place another location. And then every time it plays some, so here it called macros at a time. And then in the end, it attempts something. So here like as capital T indicate that's the end of this episode. So we could consider it as a game as well. So and then finally we receive some reward. So I don't really know what the real metric is, but I think after people can formalize the problem into decision making or into reinforcement learning framework. So for example, each time step, it can give some reward, and the agent will give some action. And in this kind of framework, and then finally it will give a like the final reward, what the agent would like to achieve. Inside this framework, like the agent can be trained to achieve what it is told to do. And another example is architecture search. So it's an recent advanced topic in the field of like neural network architecture. So the initial framework is published like many years ago, but it's still a very active research field. So here is that the high level concept is that you can train a controller, which is actually an reinforcement learning agent as well. So it can really like given some reward. The reward is that the system can formalize or propose some new neural network architecture. The system will run this kind of new architecture on a data set, maybe like Cipher 10 or ImageNet. It can attain certain rewards for example, whether it increased the accuracy performance compared to the previous iteration of architectures. Use this as reward. It can feed back to the controller, which is the agent. It can decide what kind of action to take on the next time step. And then it complete a loop between the agent and this kind of abstract environment, I would say. So you can, so here is a great example to use reinforcement learning as a really general decision-making tool. So it can help the people or like developers to, because like designing the neural network architecture is a highly skillful task. So using reinforcement learning in this framework by like formalizing what kind of goal it would like to achieve, which in the form of reward, and also to give it like some available actions, the reinforcement agent can learn to achieve this goal by the interaction themselves. So the third application is on robotics. So it's a very active research in robotics in the recent years to use like deep reinforcement learning to help like the robot to adapt in different input and scenarios. So here the figure are showing that like many different robot arms, they are running in parallel, and the task is doing is that to recognize some item. So it will given the robot arm is given certain instruction to pick up like certain object. Like for this one, it will recognize one object and then pick it up. So it complete this task. And for all of the other robot arms, they are given like different objects as the goal. So as long as the robot arm pick up the object, the reward will be maybe like +1, and then so that all of the arms, they are training the same agent to achieve this goal. And using reinforcement learning, it can help like the robot arm to adapt in different inputs. For example, if you change the location of the objects, the agent can still recognize where to operate on the object. And another one is like to train it's a very recent work, I think just a few months ago from Facebook AI. So they train the robot in simulation and then to adapt this robot in different real world scenarios. So this is a very tricky one. So I think what they shown here is that in an alternative way is to use like control mechanisms in the classic robotics. So they can just hand tune the robot like parameters in different scenarios to make them work in different like field conditions. However, like this new work, they show that with an agent trained in simulation scenario, you can still easily apply it in the real world applications as well. So these are just some like showcases of like what reinforcement learning can do beyond the video games, because I think many of the people have some misunderstanding that reinforcement learning can be only used in training video games, but I think that's not the case. The field has really go far beyond video games. Cool. Yeah, any questions on the applications? We won't go to much technical details, but like on a high level understanding on why reinforcement can be used here. All good. So let's continue. So, okay, one questions. How to speed up reinforcement learning? Yes, there are many different ways. I can talk some of them in the second part of the lecture, like tomorrow afternoon, Singapore time, and like which include like as I mentioned in the let me go back a bit. So in this kind of large scale video games and distributed training system, some of the typical way is to really run many of the game instances to collect as many experience as possible and to collect them as fast as possible. So that like heavily rely on like the distributed training system. So that's one aspect to improve the training speed. Another aspect to improve the training speed is to innovate in the reinforcement learning algorithms. So we will also talk about that in the second part of the lecture as well. On the first part, I think we will only go through the key concepts and some core ideas in the traditional reinforcement learning sense. Yeah, cool. Is that clear? Yeah, cool. So let's continue with the key concepts in reinforcement learning. This figure is very classic. So it's called the agent environment interface. It's from the Shorten and Battle book. So the reinforcement learning, the introduction to reinforcement learning book I mentioned in the very first slides. It really captured the central idea, and I think many of the concepts I already briefly touched in the previous sessions. So here we can see like there are two major like instances here. First one is agent, the other one is environment. So the agent is, so there are many instantiations of the agent. As I mentioned, they can be a robot, they can be the AI which is playing the game. And for the environment as well, so the environment can be the real world situation, and also it can be like in the simulator, like in the game engine, or like any very specific like local part of the world. For example, in my room and just on top of my working desk. So it can be a very small concept, or it can be a big concept of like the whole world, or like or the environment can be like the trading market, or like it can be I think like anything. Like you can define the environment. It can be virtual, it can be real. So the framework is really general. And as you can see here, I highlight a loop of how the agent and environment interact. So we will expand this. So here are some definitions. Let's see here. So the first step, so it's a loop. So it will be like recursively run through these steps. First one is like at time step t. So let's define a time step t. It can be general, so it can start from 0 or from like 100 steps or anything. So at any time step t, the agent receive a state st from the environment. So the environment will give a state to the agent. So it's this arrow, right? And then based on this state, the agent will make decision and then produce an action AT. The action AT will be feedback to the environment. So that so it's like in the video game, the state here, you can think it as the pixel screen input to the model. And then based on this pixel screen input, the agent can produce some decision. So for example, in the game of Breakout, it can produce an action of like go left or go right. So these are the action AT. So the action will be feedback to the environment. So it's like the human player, you press the button, and then it will give it back to the game engine. So here is the environment. And then when it receives this action from the agent, the environment will produce like a reward on the next time step. So we are following the convention in the book. There are other conventions as well. So here, like the results of the action at time step t will produce a signal of reward at next time step. And also at the same time, the environment will transit into the another state. So for example, if in the breakout example, if you move the pedal to the left, the environment will change the screen pixel. So it will feed the next time step screen to the agent again. And then this loop will just like go into a iterative loop until the environment stop. So in certain definition of the loop, it can really like when it stop, when for example, when the AI loses the life in playing the game, it can restart the game, just like human players playing the video games. It can restart, and also to but the agent is like, but already, the agent already learned something from the previous interaction. The environment can restart, and then the loop will still like go again. So, and then we can define a very key concept in reinforcement learning as a trajectory. A trajectory means the loop, like when the agent environment loop, when it go around, it can produce like certain key variables, as we mentioned, like state, action, rewards, and then next state, next action, next reward, and so on. So it can like the trajectory can be various lengths, but it is of the data we can say produced during these interactions between the agent and the environment. So this slide will answer a question raised before. So when does the model or like the environment knows that the game ends? So it is called like episodic tasks. So the definition of episodic environment is that it can have a terminal state. So which means that the environment ends there. So here are some brief examples about how an episodic environment can look like. So the first one is like the environment ends at a win or loss state. So for example, in the game of Go, so when one of the player, either of the player wins, the game will end. So that's a very natural definition of an episodic environment. Also, on the second one is like sometimes we can specify a fixed number of time steps. The environment will be answered. So it's like given some time budget for the agent environment interaction. For example, we can say the robot can operate in like 5 minutes, and then and the goal is for the robot to walk to the kitchen. So if the robot, like I think we can define in this way, like 5 minutes, we can translate into the number of time steps as well. And then if the robot reaches the kitchen, the pre-specified goal within the time, it will receive a reward +1. Otherwise, it would be like -1 or even larger penalty. So that's also a very like classic definition of some episodic game as well. Also, the environment can end with certain condition. Actually, I already mentioned one example in the second one, the robot reaching kitchen case. If it reaches the kitchen, it can end the environment because it can already produce the positive reward. So even it is before the fixed number of time steps. So here are 3 like classic conditions which form some typical episodic environments. And under the episodic environment, we can have a cumulative return. So we are following the definition of the Shelton and Bartle book. So the return at time step t is defined as the sum of all the rewards in the future. So from time step t going forward, t plus 1, t plus 2, all of them until the end of the task. So the ending condition can be any of these, but we denote the ending time step as capital T. So the cumulative return is essentially like what from the current time step, what the agent can collect from the environment. So the total sum of all of the reward it can collect. There's another type of tasks and also very important concept called discounting. So another type of environments, they are called very different from the episodic tasks. They are called continuing environments. So I think in a high level, it means like the task does not end at a certain time step or at a certain condition. So you can think it as like the time go to infinity. For example, here like it's a dot instead of like fixed time step t. So some examples here is include like the robot experience with in the surrounding environment, like unstoppedly, so it can just wandering around. It's not given any fixed like time budget or any specific goal. So it can just wandering around doing whatever it like and keep perceiving the world and making some decision by itself. So the other one is the real world scenarios, just like what we have been doing every day. So it's not, we will not define like really the end of the date as a sole episode. We have much longer goal. For example, when you attend the school, you would like to graduate with a high like GPA and then find a good job, or you could go to like a PhD study, and then beyond that, you will become a researcher. And then that would be a very long continuing process. So here, to capture the continuing tasks, we cannot really use the like this way because it will sum of the rewards together. And like imagine that every day you receive a reward plus 1, when you sum it to infinity, like any cumulative reward will be infinity. So it does not make sense to maximize such a return. Instead, like we define classic term in reinforcement learning, which is called cumulative discounted reward. So it's very similar to the previous one, but in addition, we have a new concept called discounting. So it is denoted as the gamma parameters here. So the idea is that so here is in the time step t. So when the time is going further from the current time step, the impact to this time step would be considered as like smaller and smaller. So the typical value of gamma can be like 0.5 or like 0.9 or 0.99, something like that. And you can see like it would be like square and then also cubic and also to the power of k here in a general term. So as you can imagine, with this kind of value, especially like a low value of 0.5, if you give it to the power of like 100, the reward on the very long horizon and later stages will disappear in the calculation of the cumulative discounted sum. So here it really helps to like instead of using this unstable formulation of the total reward, using discounting can really help specify the objective of the reinforcement learning. And also it can capture the concept of time, because like you can think it as like the current action has less and less impact to the later result or reward, and it can catch up by the concept of discounting. Yeah, so again, here is the discounting concept. There are two terms here. The first one is myopic, so which means like the agent only cares about very few time steps ahead. For example, we can take a very extreme case. The gamma can be 0. So if you take gamma as 0, so the objective we are trying to optimize, so the sum of the reward here, so it's the GT, it will just become the reward of next time step. So the agent will try to just consider the immediately next time step instead of considering any reward after that. So with the gamma of really low value, like 0, it will just ignore all of the time steps following. So only focusing on the immediately next time step. So this phenomenon is called myopic. And the other case is like farsighted. You can think it as another extreme case is that the gamma, discounting gamma, is nearly 1. So you can think it as like 0.99 or even 0.995 as some like classic discounting values. They can help the objective of like discounted sum G to really capture like the reward of many time steps away. So for example, if you use like 0.99, you can see it will capture the RT plus 1 here. Also with the square of the 0.99, still a high value, so you can capture the rewards RT plus 3 as well. But with like thinking as like 100 steps later, like the K equal to 100 here, it would like have a barrier effect if the rewards happen like so many steps away. So it helps to really balance the agent to have a like a sequence of decisions and also the concept of time. No. Yeah, the question is it possible that gamma is larger than 1? No, because that doesn't sound reasonable, I think. Can you think about it? Like if your gamma is larger than 1, it means like your like really the further reward has bigger impact than the immediate reward. If gamma equal to 1, it may diverge. Yes, it must. Yeah, because you can see it is the time will go to infinite. Cool. Is that clear?
Sorry, excuse me. I cannot want to ask, what if the difficulty of the game becomes more and more difficult, and the reward can actually increasing as you go into the deeper level of the game? Is it possible?
Do you mean, can you clarify a bit? So do you mean that?
I mean, the gamma value can be larger than 1 when like the game is getting more and more difficult, and the reward can like increase a little bit.
Yeah, actually, like
just like a scenario.
Yes.
Period.
So the scenario described is correct. And actually, I have a paper which does something similar like that. So it's like the gamma can start from myopic, for example, like 0.5 or 0.8. And it when the agent is really weak, because like when it's weak, you can train it to do some myopic tasks to help the agent to grow some basic skills. And then later when it becomes more capable, you can increase the gamma to like 0.99 or even 0.995 to make it stronger and stronger. But unfortunately, it cannot go beyond 1, as we just discussed. It will diverge and it will have many other issues, and also it does not make sense because the impact of the current time will decrease along the time instead of like increase along the time.
Okay, thank you so much.
Yes, I think yes, in the June chat, the comment, yes. So let's continue. Yeah, cool. So here again, so we are still discussing the return. So it's the defined as the recursive form of like the cumulative discounted sum of the reward. So the first formulation is saying the same thing as the previous one, right? So here is hello. Okay, another question. Can we normalize summation for maximum instead of using gamma? There are no, actually no. So still the definition of the total return is really general. So it's not really because it can go so if you use a gamma larger than 1, so the summation will lead the total return go to infinity if you are in a really long time horizon. So it's not about like the maximum value. So it's about the mathematical definition of the return. Yeah, so let's continue. So this equation is saying a very key form of the reinforcement learning is a recursive form of the return. So the first formulation is the same as the previous slide. And then we can like just extract the gamma. And then you can immediately see like all of these like gamma becomes like the power of the gamma become like 1 less. And then you can summarize this part using the return of the next time step. So finally, we obtain like this formulation. So it's the return of t time step equal to the reward of the time step t+1 plus discounted return of the t+1 time step. So here is like this equation is the very like key recursive form in reinforcement learning, which means that you can it indicates that you can summarize the future cumulative rewards with certain variables, and then it can formalize the current time step using the successive time steps. So the overall objective of reinforcement learning is to really maximize cumulative rewards. So essentially is to maximize the GT here. Yeah. So this is a very important concept. And yeah, I think we will iterate it again and again. Okay. There are some more like very key concepts in reinforcement learning. The first one, I would say arguably the most essential one, is the value function. So the value function, the formal definition of the value function is that the value function of a state S under the policy pi is defined as the expected value of the return. So essentially, like value function of S is the expected value of the return starting from S. So you can think it as in some informal definition is that the value function of the current state S under the policy pi. You can think it as like it really is predicting if you are still following the policy pi going to the future, what's the expectation of the total cumulative reward. So this is what the equation is saying. And the later part of the equation is just changing the GT into the discounted sum form. Yeah. So this one is the really key concept. As you can imagine, if we have the value function, an accurate value function, we can really check like what's the predicted like win rate if we use the go ball as an example. You can give certain position of the black and white as an input to the value function, and the goal of the value function is to really it can predict, right? Because it's doing the expectation and also is allowing the policy to run through the whole game. And then what it can do is that it can, based on the current position, to predict the end and also to sum of the reward with discounting in between. So with so you can have like the current position as input, and then you can have a win rate. So it's like in the current position, given this policy, it can win. So you can just obtain the predicted the predicted win rate of this policy, and then you can decide like whether the policy is good enough, or you can decide like whether the current state is good or not. So informally, you can think it as like really evaluating the policy. So evaluating the pi. Yeah. So the value function is also called the state value function. So because it's taking the state as input. There's another value function called action value function. So the formal definition is actually quite similar to the state value function. With one difference is that it's taking the action as consideration. So the formal definition of the action value function Q pi SA is that if the agents start from the state S and take an action A, what's the expectation of the total cumulative reward? So it's very similar to the definition of value function, but it takes the action as consideration. Yeah. So in informal sense, you can think it as like it's evaluating this policy and also evaluating the state and the action. So imagine that you have the action value of action like 0, action 1, and action 10. You can just rank these like these Q values, so or like action values. You can rank them under the same state, and then you can choose the best actions just according to the sorting. Choose the maximum of the Q values so that you can have the best action for the expectation. Another question? The rewards computed based on the state of the action. No. So the question is the reward is computed based on the state of the action in the first place? No, the reward is given by the environment. So the reward is not computed by the agent. Yeah, let's continue. So here we comes to the really core idea in the value function computation, and also very essential concept in reinforcement learning is called Bellman equations. So for people who are familiar with like dynamic programming, so it's I think it's very similar, and the key concept is from the dynamic programming as well. So here we can go through these equations line by line. So the value function is defined as the expectation of the total return, right? So, and according to the recursive form of the return, we can expand the return of the current time step to the reward of the next time step plus the discounted of the return of the time step t plus 1. Yeah. So this is like just natural expansion of the definition, and also a recursive definition of the return. And then later, we can incorporate the like transition. So which means like, so let me go through this. So this one is the transition from the state to the next state S prime. And with an action, it can get some reward. So this is describing how it transits from certain state given action to the next state, and it will give some reward. So for the later part of the equation, it's basically like the same thing here. So it's the reward of the next time step, right? And also the gamma discounting of the return. The return can be formalized just as so the expectation can move to the return, and then it can be put here. So all of them are captured by the, because here, like here is the expectation of the whole policy. You can expand that as the, given the state, the current state, you have different action outputs, and each of them is a probability of the policy. So by doing the summation over all of the actions, you can attain the expectation. So, and then for the next line, it's basically like just like, because on this line, we just mentioned the expectation is moved to the return. And then the expectation of the return is essentially the value function. This is the definition of a value function. So hence we obtain a recursive definition of the value function between the state and the next state. So you can see like there, apart from this transition from the environment, all of the rest is only the value functions. So this defines the, so similarly to how it recursively defined the return function, here we define the recursive form of the value function. And another concept of in the value function is called optimal value function. So the value function define a partial order over policies, which means that you can use so all of the available state, and then you use different policy like pi1, pi2, and with the value function, you can evaluate like which policy is better. So, and then with this kind of partial orders over the policies, essentially you can have a like optimal value function, which we denote as V star here. The definition of the optimal value function is that it is the value function of the best policy. So as the definition here, like over all of the policies, the largest value of the largest value of the value function over the state is defined as the optimal value functions. Similarly, the optimal action value function is defined as like the maximum Q values over all of the available policies. And then there's a relationship between the optimal action value function and the optimal value function, because like if the value function is optimal, you can easily attain like the future state can be summarized with the value functions. So you do not need to execute the policy to the end of the environment. You can just use the optimal value function to denote all of the future sum of the rewards. Yeah, I think due to the time, I will not go to the details for this one, but it's also a very important concept of the Bellman optimality function, which you can see here, like very similar to the previous Bellman equations. The value function over the policy pi becomes the optimal value function here. So you can see like it defines the recursive definition between the optimal value of the current state S and the optimal value of the next time step S prime. Yeah, similarly for the action value function, we have similar recursive form. Okay, so we will now like zoom back to like taking an overview look of on the agent components. So we mentioned like agent and the environment many times. Let's now like zoom into the reinforcement agent to see what kind of components they consist. So these are a very general definition. So an agent may include one or more of these following components. The first one is the policy. So it is the agent's behavior function. So we will expand that a bit later in the slides. And also for the value function, we just talk about that a lot. So the value function defines how good is each state or the action is. Yeah. Also, finally, a model. So the model, the concept of model in reinforcement is a bit different from in general machine learning or in deep learning. So the model here has very specific meaning of the agent's representation of the environment. So the model essentially captures the property and the understanding of the agent of the environment. We will expand it. Here, the first one is the policy. So the policy is the agent's behavior. So it defines like how the agent interacts with the environment. Formally, I think the policy is a mapping from the state to action. For example, this one is called deterministic policy, which means that we have a fixed mapping from a state to the action A with the policy function pi. Another possibility of the policy, and it is I think the most widely used one, is the stochastic policy, which defines a probability of the distribution. So here you can see that the policy is defined as like taking an input of S state and then produce an action, but it's in a distribution way. So it's defined a class example is a softmax distribution. So it can define like a probability of, for example, we have two actions. First action can have probability of like 20%. The other is like 80%. And then instead of like always choosing the second action because it has the larger probability, we will just follow the distribution of like 20%, 80% to sample this action. So that is called the stochastic policy. Also, the second one is the value. So I think we already talked this a lot in the previous slides. So it is mainly to use to evaluate the goodness or the badness of the state. And also the very important property of a value function is that it's a prediction of the future. And very importantly, the agent can use this prediction and based on this prediction to iterate through the the learning of the values. So that's a very key concept we will introduce later called bootstrapping. And also like the value, this one here I meant for the action value function, we can use the ranking of the action value function or the distribution of the action value function to sample the and choose the best action of the current state. A model, the third part of the sum of the agent component is called a model. So the model is a prediction of what the environment will do next from the agent. So there are two key parts of the prediction. First one is to predict the next state, which means like for example, this equation is given the current state S and the current action A to predict the next state as t plus 1. The other one is for predicting the next immediate reward. So except from predicting the next transition state, also the model can predict the reward. So very similarly, given the current state S and the current action A, the model of reward will predict the expectation of the next time step reward. And to give a very simple illustration and concrete example of this agent concept, we have this maze example. So there's few definitions here. First one is the reward is defined as a negative one per time step. So every time step in the environment, it will occur a negative reward. And the actions are only 4 different kinds of action. There's the 4 directions the agent can move. And the state is the agent's location. So the agent starts from this location, and then when it reach this goal, the game will end. Or it reach preset timeout duration, the game will end as well. So let's take a look on what's the key concepts of the policy and value and model they are reflecting in this simple example. So the first one is a policy. So the policy here is each of the arrow in the maze is indicating an action the agent would take when it is located on that grid. So this defined a policy, because on every given state, it can output an action. And also it's a deterministic policy because for every single state, it only has one single output of the action. And the beauty of reinforcement learning is that even you use some random policy inside the environment, so it can still evaluate the random policy to obtain the value function of this policy to understand the environment. And so you can use the random policy, collect data, and also you can just perform learning from some random and gradually growing capability policies. So instead of in other field of supervised learning or in other applications, typically the learning agent or the learning models has to take the perfect answer as input. Instead, like in reinforcement learning, we can really use any policy to achieve some learning. And here is an example of the value function. As we can see here, like per time step, the reward is -1. So it's basically, so what it is asking is actually the question is asking is that to take the least steps to go from the starting point to the goal. So it is actually a shortest path problem. And for the value, I think you can go back from the goal to the start. You can really just really calculate the value, because it's I think the connection of this maze is quite simple. So this is the end of the game, right? So it's by some convenient definition of the terminal state, it has a 0 value, and then you can go one time step back with one like -1 reward. And here the example for simplicity, we do not consider the discounting. And then each time step back, you will have an additional like -1 reward, and then you can go all the way here. And then like what it tells us is that you can really, when you go to like, for example, in this state, the agent may have to choose what kind of next time step to go with, right? So obviously, for the upper grid, it has a -14 value, and then for the bottom grid, it has a -16 value. And how the value function can help the agent to make decision is that if it has the transition model of the environment, or given the environment fully access to the environment information, it can really just compare to the value of different state. And then it can easily tell like this state is better than this state when it is choosing these two actions. And then it can go all the way here, like to the -11. And then again, it can compare just these two states. It mainly know like this is the optimal path. And for the model, I think we are here like is using a very simple example because it's not really predicting the transition. The transition is we consider it as given because the environment dynamics is given. Here is just showing if you were to predict each of the reward, it will be all -1, because even you learn the model from the environment data, all of the intermediate reward is -1. Yeah, next is some categories of reinforcement algorithms. There are like actually many definitions of how to divide these reinforcement algorithms, but I think there are some classic versions of that, but different researchers have different opinions. Here are like, I think 2 examples. First one is like divide the algorithms in the form of like how they explicitly parameterize the value or the policy. So the first category is called the value-based method. So in this kind of reinforcement algorithms with value-based methods, the algorithm will be using value function only without explicitly parameterize the policy. So in comparison, a policy-based method, the algorithm will be using explicit policy function, and yeah, so it will explicitly parameterize like the pi of a given s without the value function. And another one is like a combination of these two. It's called additive methods. So they will be utilizing like both value function and the policies. And another way to categorize the different reinforcement algorithm is using to see whether the algorithm used the model or not. So if the algorithm is not modeling the environment, it is called model-free algorithms. And if the algorithm is relying on the modeling of the environments and it predict the next reward and also the next state, it is called the model-based algorithms. Yeah, this slide is like, I think we are iterating some of the key points we mentioned earlier. So after understanding some of the key concepts of reinforcement learning, we can revisit these few points. So what really makes reinforcement learning different and interesting? So first one is like, there's no supervisor. So it's no oracle behavior or oracle answers. All the reinforcement learning, definition of the reinforcement learning, and also all of the training scenario, the agent is only given the reward signal. So without giving the optimal behavior. Another key thing is that the feedback is delayed. So like the reward is not immediately, or also like the objective of the optimization is actually the sum of the future rewards instead of like the instant next rewards. So third point is like time really matters because of the decision, they are sequential, and certain decisions in the early stage may affect the concurrences of the agent and where the agent is or what the agent is going to perceive in the much later stages. And essentially, like the fourth point, I'm saying the same thing because the agent can add to affect what it receives in the later stage. So this is also what really defines reinforcement learning, because the agent, so the data received actually depending on the agent itself, instead of like in the passive learning way, such as the ImageNet example. So the model is only trained to like classify predefined labels, instead of like the agent here can actively change the data string it is going to receive. Yeah, so yeah, for actually the final part of the key concept introduction, it is one of the key problems in reinforcement learning. It's called exploration and exploitation. So this is a very important concept, but here I'm going to only touch a very simple example to help people understand why this is important. So the example setup is like this. So the agent starts from this state, and then the action it can take is to go left or go right. Yeah, and then for the leftmost state, for this one, the agent, when it reaches this state, it will attain a reward signal of +1. And when it goes to the far right state, it will receive a much bigger signal, +100. And then if you imagine like you start to train this agent, like without telling you what kind of algorithm it's going to use, you can think as a quite likely in a very high chance, the agent will just like, first of all, it will just randomly walk to left or right. And then in a much higher chance, it will hit this state and then attain a signal. The first ever positive signal reward, like +1. For all of the other states, it is all like 0 reward. So when it hit the positive reward, the agent learns like the left, going to left is good. And then if it really like exploit this, what it is learned, it will always go to left. So without ever trying the action right. So if we do not deal with this problem, the agent kind of like overfit to the left action to always to reach this like actually less signal in the long term. So if the agent instead to like give out what it is learned, it is good, like going left is good, right? Because it can hit the positive signal very easily. Instead, it should try to go to right. And then just a little bit further, it can reach a much larger positive signal. So if the agent like only exploit what is learned, in this case, always go to left. It cannot reach the optimal solution. So what it means like it has to explore. Exploration means that the agent should every so often to go to some of the state the agent hasn't visited before and try some of the actions it hadn't learned to be good yet. Because the interesting part of reinforcement learning is that it really like time matters. Like it's not like in 2 steps it can reach one positive reward. That's the optimal. So that's not the case. So because like in a much longer time test, it had a much bigger reward. So because of this nature of the reinforcement learning problem, the agent has to learn how to balance exploitation and exploration. Like there are many algorithms on that. And some of the like very simplest one and also very effective one is called epsilon greedy. So epsilon greedy is essentially like typically the agent will take the greedy policy, which is the in the Q action value cases, you can figure as the greedy policy is the one, which is the taking the action with the maximum action value function. Because according to the definition of the action value function, the higher value the action value function is, the better the action is. So with a greedy solution, the agent would choose the action with the highest value. In this case, like it will go to left. If perform a few steps of the learning. Instead, epsilon greedy is saying that every so often, like with certain probability, for example, like 5%, a very small number of probability, even actually the actual use the probability in the actual reinforcement learning training is even smaller, like 1%. So with a small probability, the agent would try the other actions randomly. So here, in this case, it will try right every so often. And then along the training, the agent would eventually reach this point. And then to see, okay, the agent now get it. There's much better reward on the right. And the agent will learn to go to this optimal path instead. So here is just a very simple illustration of this problem. And actually, there are many much more difficult scenarios in reinforcement learning. But I think hopefully this helps people to understand exploration and exploitation a bit. Yeah. Okay. So I think actually I have more slides on the first part, but I think probably we should pause here